With the permission of the doctorate board and in order to obtain the degree of doctor from Radboud University Nijmegen, I would like to defend in public my dissertation entitled Flexible Time-to-Event Models for Complex Infectious Disease Data. My journey into time-to-event modeling began with the Cox model 16 years ago and allowed for some fancy photos of myself to become public, including a selfie with Sir David Cox himself. Time-to-event models aim to model how risk factors affect the hazard rate for a particular event of interest over time. The hazard rate is the instantaneous rate of an event occurring at a given time, given that it had not occurred before. Loosely, the hazard rate can be associated with risk. For example, here, we expect a higher risk for an event at 6 months compared to 18 months for all individuals who were event-free before those times. The Cox proportional hazards model is the most popular time-to-event regression model, mainly due to its efficiency. Without needing to specify any formula for the hazard, over time, it allows one to estimate the hazard ratio, which is the hazard rate for one group divided by another group, say boys versus girls. It does this by making a simple assumption that the hazard ratio is constant over time. The Cox model gained popularity due to its efficiency. But efficiency in regards to computational differences in models is different from when the Cox model was published in 1972 to now. An understanding of the hazard rate over time may be important. For example, it's important to know when the peak hazard occurs. There are models that have been developed that estimate flexible shapes of the hazards, and the computational speed may not be noticeably longer than that of the Cox model. These flexible models may additionally allow non-constant hazard ratios, amongst other things. For example, we could show a large effect at age 3 months or no effect at age 24 months. One such model is the piecewise exponential additive mixed model, or the PAM. The PAM can easily estimate the baseline hazards in addition to other complex risk factor effects. Of course, the choice for more complex model depends on the data complexities too. In this thesis, we extend the PAM to a framework of recurrent events to flexibly estimate the hazards and risk factor effects and apply this to data from pneumonia and malaria birth cohorts in Africa. We incorporated this methodological extension into an R package called PAM Tools. Additionally, we apply the PAM in a competing risk setup to malaria data to understand how risk factors may affect the hazard rate of a malaria infection in a human becoming potentially infectious to mosquitoes. We do this while accounting for malaria infections that spontaneously clear. In addition, we account for double interval censoring. We do this by developing a novel model where we flexibly estimate the hazard rate over time, but we make the simple Cox's assumption of proportional hazards. Pneumonia is a major cause of death in African children under the age of 5. In the Darkenstein Child Health Study in South Africa, it was seen that pneumonia episodes reoccur in about 20% of the cohort within the first 2 years of life, increasing the likelihood of future lung-related health issues. Recurrent events are a special type of time-to-event data, since the event times may be correlated. You can imagine that a child's lungs could be weakened after just a single episode of pneumonia, making them more susceptible to future pneumonia episodes. Commonly used models for recurrent events extend the Cox model to account for this correlation, but they maintain the Cox's assumptions of proportional hazards over time, or constant hazard ratios, and no estimation of the absolute hazard. The PAM allows for the hazard rates and time-varying effects to be estimated to identify temporal risk factors. Additionally, it allows the seasonality effect to be modeled cyclically and time-varying. Some of the highlights of our findings are that pneumonia hazard peaked at around 4 months. Children who are exposed to HIV through their mothers, but they themselves are uninfected, appear to have a higher pneumonia hazard compared to children unexposed when they are very young, but this effect diminishes to an equality as the children grow older. We showed that children born in summer and autumn have peak risk at their first winter, while children born in winter or spring experience generally lower risk over time. The second infectious disease that provided methodological inspiration was malaria. Malaria is a preventable but life-threatening disease caused by parasites transmitted through mosquitoes, and about 95% of cases and deaths occur in Africa. Malaria parasites have a complicated life cycle involving humans and mosquitoes. Infected humans can infect many mosquitoes, thus making the disease difficult to eradicate in the population. The appearance of gametocytes in an infected human is indicative that the infection may be infectious to mosquitoes. We were interested in understanding how risk factors affect the hazard of gametocyte appearance over time, from the moment an infection occurs. However, some malaria infections spontaneously clear before gametocytes appear. This spontaneous clearance is a competing event, since it prevents the primary event from being observed. Ignoring this competing risk could result in biased estimates of risk factor effects. An additional and much more challenging complexity is that of double interval censored times. Individuals were followed up roughly every 4 weeks and tested for malaria parasites and gametocytes. So say at time 0, a person was parasite negative, and at time 4 weeks, they were parasite positive. They must have got some malaria somewhere in between, but we do not know exactly when. And let's say that at all times up to 8 weeks, the person had no gametocytes detected, but at 12 weeks they do. Then again, we do not know exactly when gametocytes first appeared. This is double interval censoring. First, we ignored double interval censoring and used the detection times as the event time so that we could use a competing risk PAM. One of the interesting findings is that nearly 100% of infections that persist even with a low parasite density of 1 will show gametocyte appearance in approximately 2 months. Another important finding was that infections in hosts with sickle cell trait, one abnormal gene for making hemoglobin, had a higher hazard of gametocyte appearance over time compared with infections in hosts with normal hemoglobin genes. Since the PAM cannot handle interval censoring, we developed a novel model to do so while still estimating a flexible hazard. Applying the model to the malaria data showed that the hazard for gametocyte appearance peaks at around 3 weeks after malaria infection. The cumulative incidences indicate that within 2 months, approximately 1/3 of malaria infections will have gametocyte appearance, while almost 2/3 of infections will clear without gametocytes. Complex time-to-event infectious disease data are often simplified to be applied by more commonly known methods, limiting the answers or the questions we are asking about the role of risk factors. In this thesis, we focus on developing and applying more flexible models on complex infectious disease data. Having presented the summary of my thesis, I return the floor to you, Rector.
Thank you very much.